Hey, Transatlantic AI hackers, this is Jay Burris, your OpenVINO Academic Program Manager from the Network and Edge Group at Intel. And we also have Eric Kolkaj, and he has a number of mentors to help you as well from Luxonis. Eric is a DepthAI software developer. We have 3 exciting collaborative AI-capable technologies to bring you. Number 1, the OpenVINO Toolkit, which is Intel's AI Inference Toolkit to deploy high-performance deep learning inference. It allows streamlined development and ease of use, and a write-once-deploy-anywhere methodology. You can learn more by visiting openvino.ai. Second, we have the Intel Developer Cloud. It's always installed with the latest version of the OpenVINO Toolkit. It has active learning through Jupyter Notebook tutorials, and you get up to 50 gigabytes of private storage space for your code and your data sets. Visit devcloud.intel.com to learn more. And Luxonis is bringing you the Oak D Lite device powered by the Intel Movidius VPU. This device is going to be provided to each and every one of the accepted participants in the Transatlantic AI Hackathon. Past solutions were really bulky. To combine a depth sensor, a camera, an AI processor, and a host device, you had to connect a lot of different devices, which meant a lot of discrete componentry, higher power draw, bulky form factors, and bespoke designs. Luxonis has consolidated features in one platform with their Oak D Lite DepthAI Spatial AI platform. So let's talk a bit about AI inference with Intel. Computer vision and AI is changing industries. For example, with emergency response, real-time emergency and crime response, in cities, enhancing safety, research, and more, in healthcare, revolutionizing patient outcomes. Our focus for this Transatlantic AI Hackathon is largely industrial, powering Industry 4.0 solutions. The opportunity for AI is enormous. Global AI software revenue is projected to reach $126 billion by 2025. AI hardware growth rate is expected to achieve 37.5% through 2027. AI as a service is going to be valued at $43.3 billion by 2026. And AI manufacturing is projected to exceed $16 billion by 2026. Now, there's many approaches to analytics and AI. There's really no one size fits all. There's supervised learning, unsupervised learning, semi-supervised learning, and reinforced learning. AI encompasses both machine learning and deep learning. Our focus really with OpenVINO and with the device we're providing you is in the deep learning space with image processing and the Luxonis device bringing you AI image processing as well as depth AI sensing capability. Now a little bit on the differences between machine learning and deep learning. So in classic machine learning, how do you as an engineer best fit features? Well, it might be more like looking at somebody's face and identifying the features and the roundness of face, the distance between the eyes and the nose, the eye socket depth, and so forth. And using classifier algorithms such as naive Bayes, decision trees, logistic regression to identify that this image of this person is Arjun. With deep learning deploys neural networks. They're called neural networks because they're designed to mimic how the brain functions, with all these different nodes in different layers interconnected so that the compute power can produce an output layer and identify a person not based on specific static characteristics, but based on having learned over a data set who this might be. This is applied to many different use cases in computer vision, whether it be object detection, recognition, and so forth. It doesn't have to be a face of a person. AI and computer vision are being used in lots of different use cases. Now, a little bit on convolutional neural network architectures. Now, the input is really an image, and an image usually comes in layers, typically 3, so RGB. And there's multiple layers in the model, such as convolution, ReLU, pooling, that really are developed and trained for the feature learning. And then comes the classification portion, and the flattening, and the fully connected, and the softmax to really help the convolutional neural network identify what's in the image and do so in a way that a computer can process it. Remember, a computer runs on ones and zeros, so it's somewhat linear. So we're taking an architecture that's very three-dimensional and breaking it down into a way that a computer can process it and then tell you what it's identified and what it's classifying. For a great article on this image and to understand a little bit more about convolutional neural network architectures, I encourage you to visit Towards Data Science. Sumit Saha has produced an article there. So why deep learning? Well, with image recognition, and you can see, or speech recognition, you can see the green dashed line is really the human capability, and it's fairly flat. But with image recognition and convolutional neural networks, we're now able to process images better, faster, more accurately with deep learning. And in speech recognition as well, such as play a song, identifying a song, or recognizing what you're saying to a smart device. Deep learning is allowing these devices as well to recognize speech. It's estimated that this will be a $13 trillion economic impact by 2030. But you need to have some considerations when you think about deploying AI compute. Number one, what's your workload? What's your workload profile? Number two, what are your requirements in terms of scalability, security, throughput, accuracy, efficiency, cost, power, size, reliability, and so forth? And what will your demand be? When you think about, you might need multiple architectures to meet the demand. There's a big difference between an edge device, a small maybe AI capable doorbell type camera, versus a whole data center that has a vast amount of compute. So you have to keep within your requirements. And Intel's providing architectures so that our customers and our developers can deploy a variety of architectures, even in one device, be it CPU, or tapping into the capability of an integrated GPU, or adding a discrete GPU alongside that CPU, or even a vision processing unit, a VPU, or an FPGA. So let's talk a little bit about the OpenVINO Toolkit. So as an overview, there's really kind of 3 phases to the OpenVINO Toolkit: build, optimize, and deploy. And OpenVINO supports a whole range of AI frameworks such as TensorFlow and PyTorch and Onyx and others. And with the OpenVINO Toolkit, you can deploy with the same code to Intel CPUs, Intel integrated GPUs and discrete GPUs, our VPUs, Movidius, and FPGA. I'll note that the device that we're sending you, the Luxonis Oak D Lite device, uses the Intel Movidius VPU, which was designed specifically for very low power, small form factor devices. OpenVINO can support Windows, Linux, and Mac OS on your development machine. So why choose Intel? Well, number one, we think it's important to maximize CPU typically. While we're not providing you with a CPU, we're providing you a VPU. I'm explaining the overall architecture and why Intel is leading with the OpenVINO Toolkit. The CPU generally itself in market is the most widely available architecture there is. And you can deploy AI models into applications with OpenVINO towards CPU, but you can also optimize and deploy to GPU and VPU as well. And the AI Toolkit provides optimized software, a simplified data pipeline, simplified analytics and AI support, and the ability to move and store data so that you could build leading prototypes for next generation AI solutions. There are challenges in deep learning. There's unique inference needs, for example. There could be a gap in performance and accuracy between trained models and deployed models. There's integration challenges often, so no streamlined way for end-to-end deployment workflow. And oftentimes, no one-size-fits-all, because there's diverse requirements for the myriad use cases that require different approaches, different form factors, different power envelopes that you have to fit into. Different size models. Some models are really large, so they can process large amounts of complex data. And some models are trained to be really, really small, so they can be deployed at really small devices. But what this leads to is sometimes low performing, lower accuracy deployed models. Sometimes it slows down the time to market and the inability to meet use case specific requirements. That's why the OpenVINO Toolkit was developed. It was developed to deliver high-performance deep learning inference, but to do it in a way that was a streamlined development and ease of use methodology, and to be able to write once and deploy anywhere to a whole range of compute architectures. To provide you faster, more accurate real-world results with high performance, AI and computer vision inference, deployed into production from the edge to the cloud. OpenVINO is being deployed across industries. Now, your focus of the Transatlantic AI Hackathon is really Industry 4.0, but it's being deployed in industrial use cases, so manufacturing, utilities, robotics. It's being deployed in health and life sciences to improve patient care and enhance medical diagnoses. It's being deployed in retail with computer vision and natural language combined, smart kiosks and checkouts. It's also being deployed in safety and security to help improve public safety with deep learning. Smart cities are deploying to deliver intelligent interactive displays, smart automated attendance, and also to do traffic analysis for cities. OpenVINO is being used in media, design, and creative services. Really streamline the production of both image and audio media pipelines to deliver us the best experiences that we find today in our streaming platforms from many of the services that you probably subscribe to. It's being deployed in gaming to generate more realistic worlds and deliver responsive AI storylines. You may have heard of Stable Diffusion, for example. It's one of our Jupyter notebooks that you could check out to experience more, but that kind of model is used to really create those more realistic worlds. And it's also being deployed by cloud service providers, really to deliver this write once, deploy anywhere, because they typically deploy multiple architectures such as CPUs and GPUs and accelerators together. Now, I mentioned that there's 3 stages to the OpenVINO Toolkit: build, optimize, and deploy. In the build stage, you want to identify a trained model or train your own model. Fortunately, we have the Open Model Zoo with over 280 open source and optimized pre-trained models. But you could certainly develop your own model and train it for a number of AI frameworks like TensorFlow, Onyx, and PyTorch. You could also further reduce the model size if you want to with the Intel Neural Network Compression Framework. It allows you to quantize and prune your trained model for TensorFlow and PyTorch, as well as Onyx, for faster training and lightweight deployments. And these models can be deployed, as I mentioned, on edge devices, but they're actually also used in network edge devices and in the network to analyze network packets, and also in the cloud oftentimes, where the cloud is really delivering media experiences or The cloud may be delivering a recommender system and analyzing images and video and speech as well to provide you the answers to questions that you may ask with speech, or to provide you selections of media that you may want to pick from some of the services that you may subscribe to. In the second phase, in the optimize phase, we're starting to get into really where the OpenVINO Toolkit starts to be used. So OpenVINO is designed to first optimize the model so it can run on Intel architectures. And it does that by having a model optimizer create what's called an intermediate representation. So it takes the trained model and it optimizes it according to Intel's architectures and the architecture's instruction set, and creates a .xml and a .bin file. We also have a couple of tools that are available to you, such as post-training optimization, with the post-training optimization toolkit to reduce the model size. There are many different model sizes like FP32, FP16, Int8, and others. FP32 typically being the largest, Int8 being a smaller one. And depending on the size of your device, you may want and need to have a smaller model size. We'll talk about the Luxonis device, but I'm just going to mention here, but I'll reinforce it a little bit later. The Myriad architecture in the Luxonis device uses an FP16. So you'll be needing to use model sizes of FP16. Now after the optimize stage, you then deploy to an application. So you build in the inference into maybe a larger application, and I'll reinforce that a little bit later. But you do that with the OpenVINO runtime, what we call the inference engine. It's a common API for C, C++, or Python, really that abstracts the lower level programming for all of these hardware types. So all of Intel's CPU architectures of Atom, Core, Xeon, the VPU architecture, the Movidius, which is inside the Luxonis Oak D Lite device. It also supports Intel GPUs, discrete and integrated. And integrated means that there's a GPU inside, oftentimes an Atom, Core, or Xeon, as well as it could be deployed to FPGA architectures. So going a little bit deeper onto this optimization and deployment, OpenVINO at its core provides the model optimizer, which is a Python-based tool to import your trained model, and you convert them to the IR format, intermediate representation. It optimizes the performance or the space for the topology and the transformations that you're going to run. It's hardware agnostic. It optimizes essentially to understand the instruction sets within Intel architectures. And it produces the .bin and the .xml for the intermediate representation. In the deployment stage, we provide the API engine or the inference engine. And I mentioned it's high level, it supports C, C++, and Python programming for a runtime API inside of an application. The interface is implemented dynamically, loading the plugin needed for the device that's on, for the architecture that's on your device. So it recognizes the architecture that is in your device and will run it to there. And it delivers best performance for each type without requiring you as the user to implement and maintain multiple code paths, meaning you don't need to write a specific code path for a CPU instruction set and another specific code path for the GPU instruction set, or VPU, or FPGA, or the GNA, which is really the speech accelerator. So then you can deploy to all of these different types of architectures with your same code. So in the build phase, I mentioned that you'll bring a trained model, you'll train your own, or you can use our open model zoo of over 280 public pre-trained models. And you can deploy that with a number of frameworks. TensorFlow and PyTorch are very, very popular, as well as Onyx. The thing about Onyx too is it opens you up to the ability to use a whole other set of AI frameworks by converting those models of those, what you see in the smaller logos, to an Onyx format and then running it with OpenVINO. In the optimize stage, we provide the model optimization. And I already mentioned about the intermediate representation that it produces, the .xml and .bin file. But the model optimizer does a few techniques: linear operation fusing, stride optimizations, and group convolutions fusing. It essentially takes your trained model, optimizes it. Sometimes it shrinks it, and sometimes you get rid of unused layers so that it will perform fastest and best. Now, to reinforce this point about the size of your model, so the Luxonis Oak D Lite device uses the Movidius architecture, and it needs an FP16. This is really important. So you might find pre-trained models in the Open Model Zoo. We typically provide both FP32 and FP16, but you can actually also take an FP32 and quantize it down to FP16. And the example code at the bottom is really how to use the model optimizer, mo.py, the Python tool, and setting the data type to FP16 of your model name that you're using, and then providing the output directory of where you want that model to be quantized and produced and stored. Now, in the deploy phase, let's talk a little bit about the inference engine and the concept of deploying AI inference inside of an application. So the larger blue circle is really your application. It typically is designed for a particular use case. It's going to store and forward and process data. It may react to requests and trigger actions. Think of a smart doorbell camera. It's typically running all the time. It's just waiting for somebody to walk by to then notify you somebody walked by or somebody's coming up to your door. And of course, there's typically a physical button for them to push as well. But the inference inside that application is really what's providing the AI capability. So you build in the OpenVINO capability into a device like that, and it provides the AI input and insights back to the greater software application, which can then, say, trigger an action to send you a text to say somebody's walked by or somebody's coming up to your door. So for example, identifying pedestrians or listening for voice commands. It could classify objects if you're deploying inference into an application that is intended to do that, or track object movements. Now, OpenVINO's Inference Engine API has a common workflow. First, you start out by creating an inference engine core object. Then you read the intermediate representation. So you read the network model. That's where the .xml and .bin file come in. You prepare your inputs and outputs, so your input blob and your output blob. You load the network to the device and create an infer request. You prepare your input frame, and by frame I mean, say, images. Or if you have a video is really just a series of frames. Models are typically designed to have input in a specific way. It can be red, green, blue, RGB. It can be in other formats as well, depending on how the model was designed by the designer. What the height and width are of the input frames as well. So you prepare your input frames and the size of them to fit the model specs. Then you run the inference and you process the results to tell you whatever it is you want that model to tell you. And it runs over and over again in an inference loop. And to use the example of a smart doorbell as well, camera-enabled doorbell with AI in it, a smart camera-enabled AI doorbell is plugged in all the time or battery-powered and just constantly looking for something to happen, somebody to come in frame so that it can send you a trigger to say, somebody's walking up to your door. The Luxonis device has a common workflow too. It's a bit simpler. So you could start with a trained model from the Open Model Zoo, download an FP16 size pre-trained model, or you can optimize and quantize a model that you trained, or using a larger model and quantize it down to FP16. Then you compile the model into what's called an inference engine blob. You set the path for the blob, so you load the blob to the Luxonis device, and then you observe the inference in action with your Luxonis OAK-D Lite device. There's a couple of pointers to articles at Luxonis's website to understand more about how to use Luxonis's DepthAI platform. Now with this joint workflow, you can start by learning Jupyter notebooks about OpenVINO on our GitHub location. It helps you install OpenVINO. It's very easy. It's less than 10 steps depending on your operating system. It's 9 for Windows and 7 for Linux. With Windows, you have to install several prerequisites typically: Python, Git, and Microsoft Visual C++. With Linux, you're not using the Microsoft aspect of that, but you're still going to use Git, and you'll use Python as well. Also, check out the Open Model Zoo with over 200 pre-trained models to do things like object detection, segmentation, even natural language processing, and more. You'll focus more on computer vision related capabilities because the Luxonis device is all about vision. Our Intel Developer Cloud as well always has the latest version of OpenVINO installed. You can upload models, or you can download models from the Open Model Zoo directly to there. You can upload your own data sets and your code, or you can code right there because you get up to 50 gigabytes of private storage space. You can develop your inference engine input blob there as well, or on your own host machine after you've installed OpenVINO. And then you can download your blob to your host device from your own developer laptop. Transfer your inference engine, network engine blob as input into the Luxonis OAK-D device, which supports 60 frames per second depth. It supports 30 frames per second color camera and 4 TOPS of AI and computer vision processing. OpenVINO also provides a number of additional tools. We have a model downloader, so you can really very easily access all the models from the Open Model Zoo through simple command line instructions. We also offer a benchmark app where you can measure performance of latency and throughput of your model. Particularly, you may want to measure the benchmarking of performance of your model before quantization and after quantization. So you can get the best performance metrics per layer and overall with the model. We also provide a deployment manager, so you can generate the optimal and minimize runtime package for your deployment and deploy with a smaller footprint. And we provide an accuracy checker if you want to still check the accuracy of the model, the original after conversion. We have training extensions. We have what we call an open model server. We also have a data management framework, and we have a neural network compression framework for training. It's a training framework for TensorFlow, PyTorch, and ONNX models to quantize them and create trained models out of that way. There's a number of resources available. We'll make sure we get these slides to you so that you can access all of these links. But you can look at sort of at a phased approach. In the qualify phase, you can use a trained model or take advantage of the Open Model Zoo. There's instructions on how to install OpenVINO, and we have a number of ways. A pip install is probably the easiest, and it's very easy to do at our GitHub location. We have links to ways to prepare, so understanding demos and tools, understanding performance, benchmarking, and of course using the Intel Developer Cloud. We have some hands-on tools with Deep Learning Workbench, reference implementations if you really want to understand maybe some examples of where OpenVINO and AI have been deployed into reference implementations, use cases, the ability to optimize your workloads with best performance and deploying. And of course, we have a number of support capabilities with our community forum. We're on Stack Overflow. We have a documentation site. We do have training available and much, much more. So visit Intel at software.intel.com/IoT. You can explore reference implementations there, so sample code, cloud connectors, and so forth. You can download free software tools. You can order development kits if you want to. For the purposes of the Transatlantic AI Hackathon, you don't need to order any development kits. We're providing you with a Luxonis OakD device. You can learn more. You can also collaborate. If you are, say, an entrepreneur and entering this hackathon, you can collaborate more with IoT Alliance partners to deploy your own solution with them, perhaps, and you can find support at our forums. Now, I like to point out that there's a lot of companies using the OpenVINO Toolkit, but the point that I'm making most is that this is a growing industry that needs your talent. So you are at the right time, in the right stage, probably of your career development, to be participating in AI. So are you ready to get started? So number one, try out the Intel Developer Cloud for the edge. Number two, try out the OpenVINO Jupyter notebooks on GitHub. And also explore Luxonis' DepthAI resources, their documentation, their GitHub repository, and their Discord community. Together, we can reimagine how people and data can change our world for the better. We look forward to seeing your creative solutions. Thank you from Intel, Luxonis, and all of our partners at the Transatlantic AI Hackathon.